So using subtraction and the simple branches can be confusing since it can be difficult to remember which preferred subtraction to perform and which branch to use. There's the additional problem that the subtraction operation overrides a register value, and you may not want that. So let's take a look at some new instructions that we can use that will simplify this process for these comparison operations of greater than or equal, less than, and less than or equal. The first thing we'll look at is a set of instructions called comparison instructions. These comparison instructions performs a subtraction without placing the result in a register. They will affect flags, but they do not place the result in a register. So these show some forms of the comparison instructions. This is going to compare a memory location against WREG, which is W0. This is going to compare two working registers. This compares a register against a 5-bit literal. These two instructions compare memory or a working register against the 0 value. In all cases, these perform a subtraction which affects flags, but the result is not stored into a register. Our preferred method for doing unsigned comparisons such as greater than equal, less than equal, will be to use the unsigned branch instructions, which test the combination of the 0 and carry flags depending upon the comparison. This instruction right here is used for a greater than comparison, and it is read as branch greater than unsigned to some location, and it tests these flag conditions. We saw in a previous slide that this is the correct flag conditions to check for a comparison of k greater than j if we did a subtraction of k minus j. This instruction is read as branch greater than or equal unsigned. It tests k or equal 1. This is read as branch less than unsigned. It tests k or equal 0. This is read as branch less than or equal unsigned. This tests this flag condition. We need to set these flag conditions by using a subtraction before we reach the branch, and we'll typically use a compare instruction to do that subtraction. This two instruction sequence illustrates how to do that. We can do a comparison of W0 to W1. This does a subtraction of W0 minus W1. This branch here is read as branch greater than unsigned to some location. This branch is going to be taken if the value in W0, the unsigned value, is greater than the unsigned value in W1. So let's revisit our C code example. That's going to be an if statement that's going to compare k greater than j and execute the if body if that's true. These are 16-bit unsigned variables. The first thing that we're going to do is we're going to do the subtraction k minus j. So we're going to move j into W0, and then we're going to use the memory form of the compare instruction when we're going to say compare k. This is going to do k minus WREG, which is W0. At this point, our flags are set, and now we need to determine our branch instruction. Remember that we need the false condition for the branch instruction. The false condition is going to be k less than or equal to j. So this is going to be a branch less than or equal unsigned to our end if. This means that we will skip around our if body if k is less than j. If this branch is not taken, it means that k is greater than j, and we want to execute the if body statements. So now let's write the assembly code for this if statement that says if k is less than j, do this if body, else let's do this else body. Both k and j are unsigned 16-bit variables. We're going to perform the subtraction of k minus j using the same manner as we previously did. Remember that this branch needs to be for the false condition, so the false condition is going to be k greater than j. This branch is read as branch greater than unsigned. This branch is taken if k is greater than j, and we're going to execute the else body statements and then execute the rest of this code. If this branch is not taken, then that means that k is less than or equal to j. We will execute the if body statements, and then we're going to need to have this unconditional branch that's going to end if, that's going to skip around the else body and pick up execution at the rest of this code following our if statement. Let's do some comparisons against a constant. Here we're comparing k against the constant. We're saying if k is greater than decimal 10, do this if body. The one way we can do it is to move k into W0, and then we can use this compare instruction here, in which we say compare W0 against its immediate value, decimal 10. The only problem of using this particular form of the compare instruction is that it's a 5-bit literal, which means it can only be in the range of 0 to 31. This particular comparison here is comparing k against 520. We cannot use the same approach for this subtraction here because this literal is too big. It's greater than 31. So in that case, we could do this. We could move the immediate value 520 in the W0, then use this form of the comparison instruction, which is going to say k minus wreg. After that, both solutions are the same. This branch instruction here needs to be for the false condition, which is going to be a less than or equal condition. So this is a branch always less than or equal unsigned, skipping the if body. We will execute this if body if the k value is greater than the constant value. So what about a chain if-else structure in which we're comparing a variable against some constant, and we're executing different code based upon that comparison? So here, if I is equal to a 1, do this, else if I is equal to 2, do this, else if I is equal to 3, do that, else the default case we're going to do that. We can write this as a C switch statement in which we say switch UA. If it's a 1, do this. If it's a 2, do this. If it's a 3, do this. If it's anything else, do this. We're missing the switch statement here because later on, when we get to the hardware portion of the course, we're going to use this switch statement form a lot, so we'll introduce it here. By the way, when you're using a switch statement, for these case statements here, you need to remember to include a break statement after each case. If you do not do that, you will fall through and begin executing this code here. Here's an implementation of the switch statement in assembly language. Here we're going to move the I variable in the wreg, and then we'll start doing the comparisons for these cases. So we'll compare w0.byte against the value 1. If it's not equal to 1, then we're going to branch to case 2. If it is equal to 1, then this branch is not taken, and we'll implement this code here, which says to increment this variable. We'll then do this break statement, which is going to be an unconditional branch to the end of the switch statement. The rest of these cases follow a similar implementation strategy. So this slide reviews all the various comparisons that we have done, and it reviews both the true branch conditions and false branch conditions for those, and shows the branch statements that you should use for all of these conditions, as well as the subtractions that you should perform in doing these comparisons. The PIC24 has various other compare instructions such as these. We're not going to use these because their functionality can be duplicated by the previously covered compare and branch instructions. So now we begin doing some complex condition testing. Here we're going to do a chain of logical AND comparisons where we have a condition test here, logical AND condition test 2, logical AND condition test N. Remember that this if body here will be executed only if all of these tests are true. If any of these tests are false, on the first false condition, we know that this if body is not going to be taken. So on the very first false condition, we're going to jump and execute the code in the else body. So let's take a look at this. So here, we're going to do a test of condition 1. If that test is false, we will immediately go ahead and jump to the else body and execute the statements in the else body. Else, if it's true, we'll continue on to the next condition, test that, and so forth. If all of these conditions are true, then we will fall through. None of these branches will be taken, and we'll execute the if body statements. We will always need a branch always here, unconditional branch always, to skip around the else body statements. So let's do a complex condition example using a logical AND. The condition is if I is less than k and j is not equal to 20, let's execute the if body, else we'll execute the else body. So our first condition to test is going to be I less than k. We first need to do the subtraction of I minus k. These two instructions will do the subtraction. At that point, we need to figure out what branch we need. If this condition is false, then we want to do the else body. So we need the false condition here. The false condition is going to be greater than or equal. So it's going to be branch greater than equal unsigned to the else body. At that point, we need to implement this next condition. So we're going to need to do this test first, and we're going to do the test by saying j minus 20. These two instructions will do that. At that point, we need to figure out what our branch instruction is. If this test is false, then we want to execute the else body. So we need the false test here. The false test for the not equal will be the equal condition. The equal condition will be true if the z flag is equal to a 1, that is if j is equal to 20. So we'll do a branch always on z flag equal to 1, on 0 to the else body, and execute the else body. If neither of these branches are taken, if we fall through here and fall through here, that means that both of these conditions are true, and then we will execute the if body statements. At this point, we're going to need a branch always, an unconditional branch to the end if to skip around the else body statements. So let's take a look at complex conditions involving the logical OR. So let's just say if condition test 1 is true, let's execute the if body. If that's not true, then we're going to test this one right here. If that is true, then we need to do the if body, and so forth. If none of these condition tests are true, if they're all false, then we're going to execute the else body. So what kind of a simulated code structure do we need to implement this? Well, for the first condition here, we need to check the true condition. If that's true, then we're going to go ahead and jump and execute our if body. If that branch is not taken, then it means that the condition was false. And then we need to test condition 2. And we need to have a branch here for the true condition. If that condition is true, then we need to do the if body. And for all of these conditions here before the last one, we'll always be doing the true condition branch so that we could jump to the if body. This very last condition here, however, we're going to need to use the branch for the false condition, because if this condition is false, then we're going to want to jump to the if body, to the else body, and execute that. If this last condition, if this branch here, which is checking the false condition, is not taken, then that would mean that that this last condition is true, and we would actually fall through and execute the if body. After executing the if body, we would need a branch always that's going to skip around the else body and execute the rest of this code. So the key thing to remember from this is that all of these conditions up until the last one is going to need the branch for the true condition, and it's going to be branching to the if body. This very last condition here is going to be testing for the false condition, and it's going to be branching to the else body. This approach can be a little confusing because the last branch condition is on the false condition while all of the rest of these are on the true condition. An alternate solution to this is to use true conditions for all branches and simply follow the very last branch with an unconditional branch that's going to skip the if body and go straight to the else body. If you do it this way, it's going to require an extra unconditional branch in your code. You simply should use whatever method that you best understand. So let's do a complex condition example using the logical OR. So we're going to say if I is less than k, or if j is equal to p, or if q is not equal to 0, do the if body, else we're going to do the else body. All of these are 16-bit variables. This particular solution is going to use this approach here, in which the last condition is going to use the false condition for the branch to the else body. The rest of these conditions will be the true branch, and they're going to branch to the if body. So let's get started. The first condition we're going to test is going to be I less than k, so we need to do the subtraction of I minus k. We do that by these two instructions. We need the true condition that's going to branch to the if body. So branch always is a less than condition, less than unsigned to the if body. The next condition we're going to test is going to be this equality of j equal to p. So we're going to do the subtraction of j minus p. The true condition for equal is going to be whenever the z flag is set equal to a 1. We want to branch to the if body if that's true. So we can do branch always on 0 to the if body. the last condition here, we're going to want to use the false condition because we're going to want to branch to the else body if this condition is false. So the false condition that we're checking is q equal to 0. So we're going to compare q to 0. If q is equal to 0, so we do branch on 0, we're going to branch to the else body and execute the else body. If that branch is not taken, then we're going to fall through and execute the if body if q is not equal to a 0. After these if body statements, we're going to do a branch always an end if to skip the else body and pick up and execute the rest of this code. So for this example, what would we have to change if we wanted to use this approach here, in which all the conditions here are using the true branches, and we have an unconditional branch here after our last branch, after our last condition test, that's going to branch unconditionally to the else body. To do that, all we would need to do would be to change this statement right here, replace this statement with these two instructions here. In that case, we want to have a branch on the true condition. The true condition for q not equal to 0 is going to be the z flag equal to a 0. So we need a branch on not 0 to the if body. That's the true condition. We're going to follow that with a unconditional branch to the else body to execute the else body statements. So let's begin talking about looping structures. The first loop structure we'll look at is a while loop structure. A while loop is written like this: while some condition is true, execute the while body. The while body is followed by the rest of the code. Brackets are used here to enclose the while body. Note that if this condition test is false initially, the while body is never executed. So a general format in assembly language to accomplish this is the following. We'll have a label that we'll call top while that will indicate the top of our while loop. We're going to test our condition. This branch is going to branch on the false condition because the condition is false. We want to skip the while body and go to a label here in while that's going to be at the end of our while statement, and we'll execute the rest of our code. If this branch is not taken, it means that the condition is true, so we'll execute our while body statements. Once the while body is finished executing, we'll need an unconditional branch always back up to the top of this loop. So let's take a look at an example. Here we have while k is greater than j, execute the while body. All these are 16-bit unsigned variables. So here we'll test our condition by saying k minus j. This branch here needs to be the false condition. The false condition here is going to be less than or equal. So we need to branch less than or equal unsigned to go to the end of our while condition to skip the while body if this condition is false. If this branch is not taken, it means the condition is true. So we'll fall down here and begin executing our while statements, and then we're going to need an unconditional branch here back to the top of our while loop to begin the loop again. Another type of loop is the do while loop structure. It's written like this. We'll do the keyword do followed by an open bracket, the body of the do while loop, close bracket followed by the condition. If this condition is true, then we'll go back up to the top and execute this loop again. If this condition is false, then we'll fall through here and execute the rest of the code. In assembly language, our structure is going to look like this. We're going to have a label called top of the do while loop. We'll have our individual do while body loop statements here. Then we're going to test our condition. This branch here is going to be the true condition. If it's true, we want to jump back up here to the top of our do while loop. If it's false, the branch will not be taken, and we'll fall through here and we'll begin executing the rest of our code. One thing that's different about the do while from the while do is that the do while body is guaranteed to always be executed at least once, since the condition test follows do while body. You cannot write a while do loop in the same way as you do a do while. They are different loop structures. Here's an example of a do while loop. Here we're going to do while body. The condition is going to be while k is greater than j, do this loop. So here's our label for the top of our do while loop here. Here's our statements for the while body. At this point we need to test this condition, do a branch, so we'll test the condition by doing k minus j here. This condition here needs to be the true condition, which is going to be a greater than condition. So we'll do a branch greater than unsigned to the top of our do while loop. If this condition is false, that is, if k is less than or equal to j, then this branch is not taken, we'll fall through and we'll execute the rest of our code. So another common loop structure in C is a for loop. However, a for loop is simply a shorthand way of writing a while loop. If you know how to write the assembly code for a while loop, then you can always solve a for loop. So here's a typical example of a for loop. This is going to execute this statement 10 times. This is code that's only executed once at the beginning of the loop for I equals 0. This is a condition test. The loop is executed as long as this condition is true. And this is code that's executed after this loop body is done. We can convert this to a while loop by taking this code here and placing it before the while test. This condition test here becomes our while condition test, and this statement here is going to follow any of these statements in the for loop. So if you know how to do a while loop, you can always do a for loop. Finally, one last instruction we're going to discuss is the bit test instruction. The bit test instruction format we're going to examine is called bit test some memory location via some 4-bit literal. This is used for testing a single bit and operand and branching on that bit. The complement of the bit is copied to the Z flag. That means if the bit is 0, then the Z flag is true. It's a 0. If the bit is 1, then the Z flag is false. It is a 0. So what is this useful for? We will find later when we talk about the hardware portions of the processor that there are many special function registers that have single bit flags in them, and it's nice to have an instruction that could efficiently branch on the value of a single bit. So let's take a look at how we could do this using a bit test instruction. If I wanted to test a single bit in C, I would AND it with some constant value that only had a only one bit set in it. For example, this constant value 0080. If I write this in binary, there's 8 zeros, and this most significant byte, the least significant byte, is going to be a 10000000. And what this is going to do is it's going to test this bit. Well, what bit position is that? If that's going to be bit 0, 1, 2, 3, 4, 5, 6, 7. What this code is doing right here, it's testing bit number 7 of this K variable, and if it's a 1, it's going to execute the if body. If that bit number 7 is a 0, it's not going to execute the if body. So how could we implement this using the bit test instruction? It's easy. We simply say bit test K number 7. That's going to copy the complement of that bit to the Z flag. So what branch do we need? Well, in this case, if this bit is a 0 value, then we want to skip this code. So in that case, the Z flag would be true. So we're going to do a branch on Z flag being true to the end if and skip that. If this bit, if bit number 7 is a 1, we're going to want to execute this if body. If we do not take this branch, it means that bit value is non-zero, and so we'll execute this if body. There are many other forms of the bit test instruction are available. We're not going to discuss them. We're only going to discuss this single form of the bit test instruction. So we have seen that there's often many ways for accomplishing the same thing using different instruction sequences. So the question is, which method should you use? Well, that's easy. You should use the one that you understand. Do not try and memorize code sequences. If you memorize code sequences, all you'll end up accomplishing is that you will fail when you are faced with a situation different from what you have memorized. Your grade will not be penalized for inefficient code. The only thing we care about is correctness. If you have incorrect code, then we will always penalize you for incorrect code. If you have correct code, then you will receive full credit. So this finishes up our coverage of topics in Chapter 4. We talked about the bitwise logical operations and their use in clearing, setting, and complementing groups of bits. We talked about the bit set, clear, and toggle instructions. We talked about shift left and shift right instructions. We introduced the status register and concentrated on the carry and 0 flags. We talked about their use in accomplishing all these various comparisons on 8-bit and 16-bit unsigned variables. We looked at code that did conditional execution, and we finally finished up by looking at loop structures. In the next chapter, Chapter 5, we're going to introduce signed data, and we're going to extend the width of our variables to 32 bits. So problem 39 wants us to convert the C fragment to PIC24 assembly language. This says if U16K is greater than or equal to hex 400, or if U8R is equal to 0, do the if body, else do the else body. This is a 16-bit variable, unsigned 16-bit variable, and this is an unsigned 8-bit variable as per our naming conventions. So let's take a look at the solution. We're first going to want to do this test right here. So we're going to want to move hex 400 to W0. We'll then compare that against U16K. That will do K minus 400. So now our flags are set. For the logical operation, we want this condition test to be a true test, because if this is true, we want to go ahead and jump to the if body. So the true condition test is going to be a greater than or equal unsigned, and we're going to jump to the if body. If this branch is taken, if that condition is true, we'll take the branch and execute the if body. If this condition is false, then we'll fall through and do this next test. Now, this is the last test in this logical OR chain, so we're going to want to do the false condition, because if this is false, we're going to want to jump to the else body. So first of all, let's do the test. We're going to compare dot byte U8R against 0. That would do U8R minus 0. Our flags are now set. We're going to want to do the false condition branch, which is going to be not 0. So if U8R is not equal to 0, we're going to branch to our else body and execute our else body. If this branch is not taken, if we fall through, then it means that U8R is equal to 0, and we execute our if body. Our if body here, we'll put a placeholder instruction called the no op. This stands for no operation. It's an actual PIC24 instruction. It takes one instruction cycle, but it affects no registers and affects no flags. After the if body, we will need to do an unconditional branch to the end of our if statement to skip the else body. Here's our else body. We're simply going to simulate it by having a placeholder single no op instruction. This alternate solution uses a true condition branch for this last test. So this test is U8R equal to 0. So the true condition branch would be here. It'd be a branch on 0 flag being true to the if body. If we do not take this branch, it means that neither of these conditions were true. We didn't take this true branch or this true branch, so now we're here. So that means that we need to have an unconditional jump to the else body. This solution requires one more branch instruction than the previous solution. The C code for problem 41 reads, if U16K is not equal to hex 400 and U8R is greater than U8P, then execute the if body, else execute the else body. Here's a solution for this problem. First we'll do this comparison. So we need to do the test of U16K minus 400. That will set our flags. At this point, let's figure out what branch statement we need. For the logical AND operation, recall that we want this branch condition here to be the false condition, because if this test fails, we want to immediately execute the else body. So the false test is going to be the equality condition, which is going to be the 0 flag being true. So branch on 0 flag true to the else body. If we do not take this branch, it means this condition was true. So now we want to test the next condition. So first of all, we're going to have to do the subtraction R minus P, which is going to be done by these two statements. Note that the solution in the back of the book incorrectly used word operations for these two statements. This is a byte operation as indicated by this naming convention here. So we're going to do R minus P. Our flags will now be set. We're going to need the false condition for this branch. The false condition is going to be less than or equal. So we're going to do branch less than or equal to the else body. If neither of these branches are taken, then it means that both conditions are true, and we'll fall through here and execute our if body. Here, as before, we'll need an unconditional branch around the else body to the end of our if statement. The code for problem 43 is a while loop that says while U16I is not equal to U16K, execute this loop. Here's our solution. First, we need a label to mark the top of our loop. Then we're going to need to set the flags up for our branch for this test. So we're going to need to say I minus K, which is going to be accomplished by these two instructions. At this point, we need to determine what branch we need. We need a branch for the false condition, because if this condition is false, we want to skip around the loop body and go to after our loop body. So the false condition here is going to be the equal would be I equal to K. So our branch is going to be on the Z flag being true. So branch on Z flag being true to our loop in. If this branch is not taken, if we fall through the branch, then it means that I was indeed not equal to K. So at that point, we're going to execute our loop body, which is represented by a single no-op statement. At the end of our loop body, we need an unconditional jump back to the top of our loop, which is going to redo our test. It's a very common error is to forget to put this unconditional branch. Problem 45 is a do while loop that says do this loop body while U8R is not equal to 0 or U8P is less than U8Q. Before we get started, let's write some pseudo assembly language that's going to list the steps that we need. We need a label for our loop top, need our loop body statements. Then we're going to need to evaluate this first condition. We'll first set the flags by subtracting 0 from R. At this point, we need to determine what loop condition we need. Since this is a logical OR, we know that if this test is true, then we can immediately jump back up to the top of our loop body. So we need to branch on the true condition to our loop top. Similarly, for this comparison right here, we're first going to need to set the flags by subtracting Q from P. And we're also, if this test is true, we're going to branch back up to the top of our do loop. So we need a branch on the true condition to our loop top. So now let's write the assembly language. We're going to represent our loop body by a single no-op statement. To do this comparison of R against 0, we'll simply use a single instruction of compare 0.byte U8R. That'll subtract 0 from R. For this true condition branch, this is a not equal condition, so that means we're going to do a branch on not 0 back up to our loop top. For this comparison here, we first need to do subtraction. We'll do that subtraction by of P minus Q by these two instructions. For this less than comparison, the true branch, we'll go do branch on less than unsigned back to our loop top. Problem 47 is some C code that attempts to count the number of 1 bits in an 8-bit variable called UAJ. The way it's going to do this is going to have a for loop that loops 8 times. Each time through the loop, we're going to take a look at the least significant bit of J. If that value is a 1, we're going to increment a count and keep that count in K. Each time through the loop, we'll shift J to the right, so we'll move a new bit into the least significant bit. Before we do this code, let's transform this for loop into a while loop. So we'll take this guy right here, we'll move it here. This test right here is going to become the test of our while loop. This is still the body of our while loop. And then we'll take this code right here and we'll move it to the end of our while loop. Let's begin implementing this code. The first thing we're going to do is that this U8I variable is simply a loop counter for this loop, ensuring that it loops 8 times. As such, we're simply going to use a register W0 for that variable. We could have used any register. We could have also used a memory location, but we'll just use a register here. So here we're going to, so let's start. First thing we're going to do is we're going to clear U88K. We're going to clear W0, which we're going to stand for our I variable. At that point, we're ready to begin implementing our while loop. So we'll have a label standing for the top of our while loop. We now need to implement this test. So we'll do that by subtracting 8 from I. So we'll do compare that byte W0 with 8. That will set our flags. At this point, we need to determine what branch condition we need. Recall that for a while loop, we want this to be the false condition because we want to exit and skip this loop if this test is false. The false condition will be I equal to 8. If we subtract 8 from I and they're equal to each other, then the 0 flag will be set to true. So we want to do a branch on 0 to our loop exit. If we do not take this branch, then that means that I is not equal to 8. At that point, we're now ready to write the code for our if statement. Let's take a look at this conditional test in the if statement. This says if U8J bitwise AND with a 0, 1. That means that we're taking a 0, 1 and we're bitwise ANDing that with bits from J. Well, what's going to be the final result? Well, these are all zeros, so that these guys right here will be zeros. This bit right here, if the bit of J is a 1, it will be a 1. If the bit of J is a 0, it will be a 0. So all this is doing is simply testing the value of the least significant bit of J. If that least significant bit of J is a 1, then we're going to execute this if body. If it's a 0, then we're not going to execute the if body. By the way, this equal 1 is not needed in this code. It's simply redundant. Taking it out will this code will execute the same way. So how do we implement this test? Well, we saw that an easy way to do it is to use a bit test instruction. We could take J and bitwise AND it with 0, 1, but we can do it with less instructions by using a bit test instruction. So we'll do bit test dot byte U8J, the least significant bit. Now, what test do we need here? Well, we want to skip this if this bit test, if this bit is a 0. If the bit is a 0, then that means that the 0 flag will be set to a 1, will be set to a true value. So we want to skip the if body if our bit is a 0, if the Z flag is equal to a true. If the bit is a 1, then the Z flag will be cleared, and we won't take that branch, and we'll increment the if. We'll execute the if body, which is simply incrementing this K value. So here's where we're going to increment the K value. At that point, we're right here. We need to implement these two instructions. So this logical shift right dot byte U8J will shift J to the right by 1 and write the result back to J. Here we'll increment I, so we'll increment W0 and store the result back in W0. Finally, we're at the end of our loop at this point, so we need to loop back up. So here we're going to have a branch unconditional back to our loop top. And that completes the solution to this problem.